Section 7.1, Introducing Exponential Functions. So today we're going to introduce the exponential functions, and we're going to talk about characteristics of what the base exponential function looks like, and then tomorrow we'll get into transformations with exponential functions. So an exponential function is a function of the form y equals of x, where c is a constant and where c has to be greater than 0 or less than 1, or c has to be greater 1. These are functions where the variable is the exponent. So the unknown, right, your x and y values, your x value is always in the exponent value. So we're going to look at two types of exponential functions. The first one is when our c value is greater than 1. So for example, if we were to sketch the graph y equals 2 to the power of x, substituting or creating a table of values, we get the following values. If x is equal to a 3, then this would give me a value of 2 to the negative 3. And then thinking about our exponent laws from grade 10, a negative exponent tells me that I'm going to reciprocate my base. So this becomes 1 over 2 to the positive 3, and the becomes positive. So 1 over 2 cubed would give me a value of 1/8. 2 to the negative 2, again, I would reciprocate that over 2 squared, which would be 1/4. This would become 1/2, because I'm reciprocating again. 2 to the power of 0, well, anything to the power of 0 we know is always 1. 2 to the 1 would 2, 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16. So if I were to start to plot these points, when x is a negative 3, my y value is a 1/8, so a fairly small value. When x is negative 2, it's 1/4, negative 1 is 1/2, at 0 it's 1, at 1 it's 2, at 2 it's 4, 3 it's 8, 4 is 16, and so forth. So as you can see, as these values get increasingly bigger, or as x approaches infinity, our y values will also approach infinity. As our x values get increasingly smaller, so as these values approach negative infinity, we will always be reciprocating this as 1 over 2 to some power. So these values will always be approaching 0, but they will never actually equate to 0. So eventually we might have 1 over 100, 1 over 1,000, and so on. So as our x values decrease to negative infinity, this graph is going to approach our x-axis, but will actually never. And then as my values approach, x values approach positive infinity, my y value should also approach positive infinity. So this is what our base function looks like when our c value is greater than 1. And we call this an x growth. And it's an exponential growth because as my x values are increasing, my y values are also increasing. So things are growing. So now let's look at what the base function would look like if our c value is in between 0 and 1, so basically a fraction. So let's say we take a constant of 1/2 to the power of x. Same sort of idea. If our x value is negative 3, we're taking 1/2 to the power of negative 3. This negative tells me I'm going to reciprocate my base, so it becomes 2 over 1, and it becomes a positive. So essentially I'm taking 2 to the power of 3. So this gives me a y value of 8. If it's a negative 2, I'd again reciprocate this, would become 2. 2 squared would give me 4. 1/2 to the negative 1 would give me a value of 2. Power of 0, regardless of what it is, it's always 1. And then 1/2 to the 1 would be 1/2. 1/2 squared would be 1/4. 1/2 cubed would be 1/8. 1/2 to the 4th would be 1/16. So as you can kind of see, because constant is have the opposite effect of what happened in our base function here. So if we were to sketch these points at -3, we have a y value of 8, 4, 2, 1, and then so it's having the opposite effect. So as our x values decrease to -infinity, our y values are going to increase to infinity. As our x values increase to positive infinity, our y values are decreasing, getting halved each time. This value is going to approach but never actually equate to 0. So this is going to approach 0 but never actually be 0. Similar graph. Okay, so as our x values are decreasing to -infinity, our y values are approaching infinity. As our x values are increasing to positive infinity, our y values are going to approach 0. Okay, so it's a horizontal. So this x-axis represents as a horizontal asymptote. Okay, because when our c value is between 0 and 1, this exponential decay, we call it. So let's just talk common characteristics between these two things. Okay, so we want to have a good visualization of what these base graphs look like. Okay, your c value obviously isn't always going to be 2 and a 1/2 to change, but what is important is if your c value is greater than 1, it creates this shape with a horizontal asymptote at the x-axis. So the graph is approaching the x-axis and it's growing from there. If your c value is between 0 and 1, then we get this shape of a graph with as an exponential decay. As you notice, the y-intercept, regardless of this constant, whether it's a 2, 1/2, 3, 10, doesn't matter, this y-intercept will always be 1. Okay, until of course we start to transform things. Okay, there should be no x-intercepts at all. So we have y-intercepts at 1. No x-intercepts will occur as we start to transform. Will always act as a horizontal asymptote. The domain of both of these functions will always be all real numbers. The range of this will always be y is greater than 0. Okay, and of course, again, those will change as we transform them. Okay, the value of c is going to affect the steep x increases. So if this was a 3 as opposed to a 2, and steeper. If it was a 10, then it'd be even steeper. Okay. Same thing with this. If this was a 1/3, then the graph. Okay. All right. What else? And so that's what all the characteristics that we are going to talk about. So the key is to have a good idea of what these base graphs look like. Exponential growth, c value is exponential decay, c value is between 0 and 1. What you should notice is our c value is never less than 0 or never equates to 1. And so we're just going to talk about why that is. Okay, so if our c value was less than 0, okay, for example, if we had a graph that was, let's say, -2 to the power of x, well, what happens is when these exponent values are excuse me, are positive or even numbers, the y value will be positive. X is an odd number, the value will be negative. So what ends up happening is, if we were to kind of think about this graph, let's say this was to the power of 1, I'd have a point down here at -2. If this was to the power of 2, I'd have a point up here. To the power of 3, I'd have a point down here. So what happens is we get this random graph happening, and then if I went to the right, I get this random graph happening, which does not create an exponential function at all. It's just more of a randomized points. So that is why our C value always has to be greater than 0, because if it's less than 0, it actually doesn't create an exponential function at all. Okay. Also, when C equates to 1, well, that would mean we would have a function of 1 to the power of x. And if 1 to any power will always equate to 1. So what we will get a set of points that always equates to 1. And so if we get a set of points that will always equate to 1, really what this is creating, this is a linear function at y equals 1. Okay? So important things to remember: your C value always has to be positive, and it can never equal 1. Okay? If it's between 0 and 1, it's an exponential decay. If it's greater than exponential growth. So next example here, it says write the exponential function for the graph below. Okay, so what we're going to do is we're going to look at this function, and I know we're not talking about transformations at all yet. So I know the base exponential function for any exponential function is y equals c to the power of x. Okay, what I'm going to clearly identify here is substitute in a point for x and y to find out what my constant is. So I can clearly see here that I have a point here. I also have a point here. Okay. Any way you look at it, if I substitute my y value with a 5 and I substitute my x value with a 1, right? Well, technically my c value, c to 1, is just going to be c. So my constant, or think of it as your multiplication value, the other thing is, how is this changing from this point to this point? Well, my y values are being multiplied by 5, so my multiplication value is 5. Therefore, the equation of this function would simply be y equals 5 to the power of x. Okay? All right, and then lastly, example 2. Just like a word problem. It says a radioactive sample of radium Ra-225 has a half-life of 15 days. So key wording here, we're going to see this wording lots. It says half-life. This tells us our multiplication value. That's your C value of your function. The mass m in grams of Ra-225 remaining over T in 50-day intervals can be modeled using the growth below. Exponential graph below. So question A, what is the initial mass of Ra-225 in the sample, and what value does the mass of Ra-225 approach as time passes? So our initial mass means when time equates to 0, which is this point here. So our initial mass is when time equals 0, which is 1 gram. And then what value does the mass of Ra-225 approach as time passes? Well, as time passes, what the mass of my Ra-225, it is approaching 0 grams. But we'll actually never reach it. It'll just keep on getting smaller. So what are the domain and range of this function in context of the question? So even though this is my exponential growth, in context of the question, because we're relating time versus mass, there is no such thing as negative time. So our domain is actually going to start here, which is at 0. So the domain of our function would be t has to be greater than or equal to 0, where t belongs to the real numbers. Okay, and then the range also of the question, the mass starts at 1, it approaches 0, it will never actually reach 0. So our mass, which is, we're going to use this, we're going to say m has to be greater than, not equal to, just greater than 0, but less than or equal to 1, where m belongs to our real number system. All right, write the exponential decay mass of Ra225 remaining to time in 15-day intervals. So number 1 really represents 15 days, number 2 really represents 30 days, but we don't need to consider that when we're writing the function. We're just going to represent it in terms of 1, 2, 3, 4, and so on. So when I look at these points, again, my initial value is at 0, 1. So remember, our base function is always y e to the x, and then we have to figure out our c value. So 2 ways you can do this. You can either substitute in x and y, any one of these points, and solve for c, or simply figure out the multiplication value that's happening on my y's values as my x values are increasing. So it's going from 1 to 0.5 to 0.25 to 0.125. So the mass is being halved for each time interval. So that tells me my c value has to be 1/2. That's what's happening to the mass. So my equation would be 1/2 to the power of x. Or if you were related to the variables that we were talking about, would be 1/2 to the power of t. Estimate how many days it would take for Ra225 to decay to 1/30th of its original mass. So because it's an estimate, we're just gonna, one way we could do is we could just continue to break this down. So and rather than working in decimals, I'm going to think about this in fractions. So at this point, this is 1/4, which is when t is equal to 2. So at time 3, our mass is equal to 1/8, which equates to 0.125. At t4, I'm going to cut that in half again, which is 1/16. Time 5, I'm going to cut that in half again, which is about 1/32. So because it's just an estimate, this is my estimate value at t is equal to 5. And each one of these increments represents 15 days. 5 times 15 days, I'm going to get my value, which is approximately 75 days. Okay. If I wanted to be more specific, so that would be an estimate. If I wanted to find the exact number of days, then I would substitute this in my mass. And solve for my t value. Well, in order to solve this, because we've learned how to solve this exponent with a common base before in Math 20, but we can't get a common base between the 30 and the 2, so I'm just going to use my calculator to solve this for today. In my 1/30th, and then in y2 I'm going to put in my equation 1/2 to the power of x. I'm going to change my windows here a little bit to be similar to what is shown on the up here. So this is going to go to -2. I'm going to go up to 8 days. This will be -2 and mass of 2. And this can just go up by ones. All right. Oh, it's graphing something else. Okay, so it's really hard to see this line, so I'm going to change this window again. I'm going to go to -1 to, let's say, I'm going to go -0.5 to 0.5. There, now I can, here's my line at 1/30th. Here's my second equation here, and I am finding this intersection point here, which I know is approximately 5 days. So 5 for intersect. Enter, enter, enter. So the exact value would be 4.9 times 15. So a more accurate, if we multiply those two values, would be 74 days. Okay, and so that is the start of our exponential functions.